This is M. Prasant Raju. Stand before you to give a class of area moment of inertia of some standard figures of centroidal axis of xx and y directions. In the previous class of mechanics unit 4, we have discussed that the polar moment of inertia, product of inertia, and as well as the perpendicular axis theorem and radius of gyration, etc. like that. Now we are going to continue the area moment of inertia of some standard figures of centroidal axis of xx and y directions. Now, if you look at this chart or the flow diagrams, you can say here, I would like to split into the 6 columns. The first one is serial number, the second one is name of the specimen, the third one is diagram, fourth one is I_X, fifth one is I_Y, and sixth one is centroid of the particular specimen. So, if you take the first name of the specimen, which is called rectangle, the rectangle could be drawn like this. If you look at this diagram, you could observe that there are two axes. One is xx direction and yy direction, and this C is represented by centroid of this rectangle. And how to find the moment of inertia with respect to xx directions and yy directions? We have standard stipulated formulas towards the determination of area moment of inertia, that is I_X of this rectangle is 1/12 lb cube and I_Y of this rectangle is 1/12 L cube b. So let me explain what are the terms that are existing in these stipulated formulas. L is called length of the rectangle and B is called breadth of the rectangle. Similarly, if you want to find the centroid of this rectangle, we have a standard formula, that is C of L/2 comma B/2. Similarly, coming to the second specimen, which is known as triangle. If you look this triangle, my dear students, and the triangle is also be split up into the two common representations, that xx is horizontal direction and yy is vertical direction, and this B is called base of the triangle and H is called height of the triangle. So now, I would like to represent the determination of moment of inertia with respect to xx and yy axis, or I_X of this triangle is 1/36 ph cube, I_Y of this right angle triangle is 1/48 hb cube, and the centroid of this triangle is C of B/2 comma H/2. So in this particular diagram, my B represents base of the triangle and H represents height of the triangle. Now coming to the third specimen, which is known as right angle triangle. If you see this diagram, in the right angle triangle, it will also split up into the two axes, centroidal axis, that xx is the horizontal direction and yy is the vertical direction. This C represents the centroid of the right angle triangle, and B is called base of the triangle and H is called height of the right angle triangle. If you want to find the formulas of moment of inertia with respect to xx and yy directions, I have a formula that I_X of right angle triangle is 1/36 bh cube, and I_Y of this right angle triangle is 1/36 hb cube, and the determination of centroid towards this right angle triangle is C of B/3 comma H/3. Similarly, we have another three diagrams. Let them denoted by this after rectangle, triangle and right angle triangle, we have a circle, semicircle and quarter circle. Let us see that one also. Coming to the fourth specimen, which is known as circle, and the circle is represented by diagram form like this. If you take circle again, it will be divided into the two centroidal axes, that is xx direction and yy direction. This R is called radius of this circle. If you want to find the moment of inertia of this circle, we have stipulated formulas that I_X of this circle is 1/4 pi r to the power of 4 and I_Y of this circle is 1/4 pi r to the power of 4. And similarly, the centroid of this circle is C of D/2 comma D/2. As all you know that D is called diameter of the circle. And coming to the fifth specimen, which is known as semicircle like this, the semicircle is represented by like this, and in this also, if a semicircle is also divided into the two centroidal axes consisting xx and yy, my C is represented by centroid of this semicircle, and R is called radius of the semicircle, and the moment of inertia with respect to xx direction is to find by using the formula of 0.11 r to the power of 4, and the moment of inertia with respect to yy direction is find out to do the formula of 1 by 8 into pi r to the power of 4, and if you want to find the centroid of this semicircle is C of d by 2 comma 4r by 3 pi, and in this formula my d represents diameter, r is called radius of the semicircle. Coming to the sixth specimen, which is known as quarter circle. The quarter circle is represented by like this. Again, the quarter circle is divided into two major axes like xx and yy. My C is represented by centroid of this particular quarter circle. And if you want to find the moment of inertia with respect to x direction of this particular specimen quarter circle, we have a stipulated formula that 0.055 r to the power of 4, and Iy of this quarter circle is 0.055 r to the power of 4, and if you want to find the centroid of this quarter circle, we have a formula that is C of 4r by 3 pi comma 4r by 3 pi. And in this formula, my r is called radius, and the radius is one of the parameter acting major role to find the area moment of inertia with respect to xx and yy directions. And after finishing this 6 specimens followed by area moment of inertia of some standard figures of centroidal axis of xx and yy directions, now we are going to determine the area moment of inertia of integration. How we are going to find the determination of area moment of inertia? By the utilization of an operation called integration. We take one example that is called area moment of inertia of a rectangle, that we will see now. Area moment of inertia by integration. Let us see this. Area moment of inertia by integration. In order to find the area moment of inertia by integration, we take one specimen. That specimen is called rectangle. Let us see this. Example 1. The determination of AMI of a rectangle of length L and a breadth B. This is one of the important mathematical proof followed by the determination of area moment of inertia. Before we are going to do that, if I want to determine the area moment of inertia of a rectangle, I should perform this particular case into two different cases. The first case is determination of area moment of inertia I_x, and the second one is determination of area moment of inertia I_y. Let us see this. The first one is determination of I_x. Now I am going to draw to find I_x like this. If you could observe the diagram how I am drawing here so that you can get an idea. This is centroidal axis, xx, and this is yy. This is length L, and this is breadth from here to here. This is centroid. This particular part is called dy, which is a small width of element which is at a distance y from x axis, and from here to here is b/2, and from here to here is b/2. So this is the diagram. If you look at very carefully about this particular diagram, so that you can get an idea of deriving the expression for area moment of inertia. Now I would like to prove this particular diagram like this. Consider the proof of determination of I_x. Consider the rectangle of length L and a breadth B is as shown in the figure. Now, from figure, I am going to take a small elemental width dy. I am giving a specific name for this dy, which is called small elemental width. Okay. Now, consider dy is the small elemental weight with respect to x axis at a distance of y. Now I am repeating once again. Consider the rectangle of length L and a breadth B is as shown in the figure. Consider dy is the small elemental width with respect to x axis at a distance of y. Now utilization of this small width dy, we have to find the area of this small element. Let us see this. The area of this small element dA is given by dA is equal to L into dy. I can call it as equation 1. Now, utilization of this dA, we have to find what? We have to find the moment of inertia with respect to x axis. Now, the moment of inertia with respect to this small elemental width in x direction is given by dA double x. dA double x is equal to y square into dA. I can call it as equation 2. Now, substitute dA in equation 2, we will substitute. Substitute 1 in equation 2, we get di double x is equal to y square into L dy. Look at carefully how I am deriving this expression. di double x is equal to y square into L dy. Now our ultimate article is to find out the total moment of inertia of a rectangle whose length is L and breadth B with respect to x directions. That means I need I double x. So in order to get I double x, what I have to do with the help of this di double x? I should integrate this di double x from minus b by 2 to plus b by 2, then I will get I double x. That I am going to call it as the total moment of inertia. Let us see this. Now, the total moment of inertia is obtained by integrating di double x from minus b by 2 to plus b by 2 is given by I double x is equal to integral minus b by 2 to plus b by 2 di double x. Now substitute di double x we have here y square into L dy. Therefore, I double x is equal to integral minus b by 2 to plus b by 2 y square into L dy. Now, as L is constant, take out of the integral, we will get I double x is equal to L into integral minus b by 2 to plus b by 2 y square dy. After simplifying this, now I double x is equal to L into integral y square is nothing but how much? Y cube by 3. Now, L into y cube by 3 in between the limits minus b by 2 to plus b by 2. Now, I am substituting the upper limit and the lower limit. Therefore, I double x is equal to L by 3 into b cube by 8 minus of minus b cube by 8. Now, after simplifying this, we will get I double x is equal to L by 3 into b cube by 8 plus b cube by 8. Now, taking LCM to this fractions, we will get I double x is equal to L by 3 into 2b cube by 8. Now, after simplifying this, as 2 is cancelling 4 times in 8, we will get the remaining term is I double x is equal to L by 3 into b cube by 4. Now, after simplifying this, I double x is equal to 1 by 12 L b cube. This is the standard formula to find the moment of inertia with respect to xx direction, which is the most important formula to find the moment of inertia of a rectangle whose length is L and whose breadth is b with respect to xx directions. Therefore, I double x is equal to 1 by 12 L b cube. In this similar fashion, we are going to find determination of I double y. Let us see this. Determination of I double y. To determine the moment of inertia with respect to y direction, again we need a diagram. I am going to draw the diagram. See this. This is a rectangle. Now, I would like to take the xx and yy axis like this. This is called yy axis. This is xx axis. This is a centroid. I am going to take a small width of the element. Let this is denoted by say some dx, which is at a distance x, from y-axis. Now, I would like to take from axis I am going to take x like this. This is called length of the rectangle, and from here to here is b by 2, and from here to here is b by 2. If you want to split this length of this rectangle in y direction, you could write like this also. How? If you take from here to here, this is called L by 2, and from here to here is again L by 2. The total distance is how much? Length. And again from here to here is, this is called breadth b. Now, utilization of this diagram, we need to find the determination of I double y. In the similar fashion, how I am going to determine I double x? Similarly, in determining of I double y, I could take a small elemental width, but it is denoted by dx. Now, let us prove this particular derivative part. Consider the rectangle of length L and a breadth B is as shown in the figure. Consider a small elemental weight say dx is at a distance x from y axis. Now, utilization of this small elemental width dx, we need to find area. Let us see this. The area of this small elemental weight is given by dA is equal to B dx. I can call it as equation 1. Now, utilizing this area of this small element dA, again we need to find the area moment of inertia with respect to y direction. Let us see. The area moment of inertia with respect to this area dA can be written as di double y is equal to x square into dA. I can call it as equation 2. Now, we would like to find the area moment of inertia with respect to y direction. Let us see this, how it will be. The total moment of inertia is obtained by integrating di double y in between the limits from minus L by 2 to plus L by 2 is given by, how I am going to write this, I double y is equal to integral minus L by 2 to plus L by 2 di double y. Now, just I am bringing this di double y value to this here. So, I can represent this as equation 3. Now, substitute 2 in equation 3. We get I double y is equal to integral minus L by 2 to plus L by 2 into x square into dA. Now, I am bringing the value of dA to this particular equation. I will get I double y is equal to integral minus L by 2 to plus L by 2 x square into b dx. Since dA is equal to what? As we have considered in the previous, b dx. Now, in this equation, b is constant, take out of the integral, we will get I double y is equal to b into integral minus L by 2 to plus L by 2 x square dx. After simplifying this, we will get I double y is equal to b into integral x square is equal to how much? X cube by 3. Therefore, x cube by 3 in between the limits minus L by 2 to plus L by 2. Now I am simplifying this. I double y is equal to b by 3, as the denominator is here 3, take out of that particular part, we will get L by 2 whole cube minus of minus L by 2 whole cube. Now after simplifying this, we will get I double y is equal to b by 3 into L cube by 8 plus L cube by 8. If we simplify this, we will get how much? I double y is equal to b by 3 into 2L cube by 8. And if you simplify, this 2 will 4 times in 8. I will get like this. So the remaining term is equal to, we will get I double y is equal to b by 3/4, 12. That means 1 by 12 into BL cube, or we can simply write like this, after rearranging, I double y is equal to 1 by 12 L cube B, which is known as the ultimate expression for area moment of inertia of a rectangle whose length is L and whose breadth is B with respect to y axis. So in this way, we could find the determination of moment of inertia of a rectangle whose length is considered as L and whose breadth is considered as B. Then we need to find the moment of inertia with respect to x axis is determined by I double x, and the moment of inertia with respect to y axis is denoted by I double y. So in the determination of I double x, we got I double x is equal to 1 by 12 LB cube, and determination of area moment of inertia with respect to y axis, let it be denoted by I double y, that I double y is equal to 1 by 12 L cube B. In this way, we have to find the determination of I double x and I double y of the utilization of a specimen called rectangle. As I put main heading here, that the determination of AMI of a rectangle of length L and breadth B, we need to find the two important parameters. Let them denoted by I double x and I double y. I gave you very specific names for I double x and I double y. I double x is area moment of inertia of rectangle with respect to x direction, and I double y is area moment of inertia of a rectangle with respect to y axis. And after finishing this, my dear students, as we have a determination of centroid with respect to 3 simple categories in unit 3, similarly in unit 4 also, we have the determination of area moment of inertia of the 3 simple categories. The first one is AMI due to simple figures, AMI due to composite figures, and AMI due to shaded regions, that we will see now. If you look at this problem, area moment of inertia due to simple figures, as I told you in the previously, we told that area moment of inertia is usually be calculated with respect to the 3 criteria. Number 1 is simple figures, number 2 is composite figures, and number 3 is standard regions. Okay. Now, if you look at this problem 1, my dear students, I am read out the problem 1. Find the moment of inertia of a rectangular section of 30 millimeters wide and 40 millimeters height about its centroidal x and y axis. Now, if you want to do this problem, first of all, what we have to do here is, by looking through this problem, we should download the given values from the problem. So that is given length L is equal to 30 mm and breadth B is equal to 40 mm. Mm represents millimeters, and we have 2 major formulas for finding the area moment of inertia of any specimen with respect to x and y axis. The previous flow chart is telling that the specific formulas followed by I double x and I double y. In this present situation, moment of inertia of a given rectangular section with respect to x direction, we have a standard formula. What is that here? That I double x is equal to 1 by 12 LB cube. My L is called length that we have given here, and my B breadth that we have given here. Therefore, bring both of the values and substitute in this formula, we will get Ix is equal to 1 by 12 into 30 into 40 whole cube. After simplifying this, we will get Ix is like this. So what's the value of Ix here? My Ix is equal to 160000 meters to the power of 4. If you are going to convert this into meters, we will get like this. As we have given both the values in mm, that means millimeters, we are going to get the moment of inertia with respect to xx direction is Ix is equal to 160000 meter to the power of 4. Similarly, we are going to find the moment of inertia of a rectangular section with respect to yy direction, that we will see now. The second parameter, which is known as the moment of inertia of a given rectangular section with respect to yy axis, is given by Iy is equal to 1 by 12 L cube B. So, and again, as we know the given values that L is equal to 30 millimeters and B is equal to 40 millimeters, bring both the values and substitute in this formula, we will get Iy is equal to 1 by 12 into 30 whole cube into 40. And after simplifying this, we will get Iy is equal to 9 after 4 zeros mm to the power of 4. So we got huge values of determination of area moment of inertia. So there is a little bit variation with respect to the determination of centroids due to the simple figures and determination of area moment of inertia due to the simple figures. Now we will do one more problem based on T section, L section, etc. If this is the problem, if you could take, this is known as problem number 2. I am read out this problem. Find the moment of inertia of the following T section about centroidal xx axis. If you look at this problem, suppose if a problem given to us, how can we do this problem? First of all, as I told you in the unit 3 classes, that if you have given T section or L section or C section, anything else, first of all we have to apply the property of symmetry to this diagram. So how to apply the property of symmetry to this diagram? This is yy axis and this is xx axis. I am checking the property of symmetry to this T section. So my given T section is symmetric to y-axis. So when you are going to confirm that the given T section is symmetric to y-axis, x bar is equal to how much? 0. That we have to write first of all. Solution. The given T section is symmetric to y-axis, hence x bar is equal to 0. So when x bar is equal to 0, we have only one parameter which is known as what? Y bar. So first of all we will find the centroid of this T section. Let us see how it will be. Now the given T section is divided into two parts. Part 1 is called vertical rectangle and part 2 is called horizontal rectangle. In the part 1, how to find the area? By utilization of L and B. My part 1 of vertical rectangle, area A1 is equal to L into B. As we know that the given T section is split up into the two columns or two rectangles. The first part is called vertical rectangle and the second part is called horizontal rectangle. So if you see the vertical rectangle, A1 is equal to L into B, my length is 4 centimeters and my breadth is 12 centimeters, we will get 48 centimeters square. Similarly, how to find the coordinates of y1? Here in this particular T section, we need not find x coordinates, we need to find only y coordinates. Why? The given T section is symmetric to y-axis, hence x bar is equal to 0. Once in the centroid of a two parameters or two coordinates, if x bar is equal to 0, no need of finding all x coordinates, we need to find only y coordinates. So therefore, my y1 is equal to b by 2, and as I told you that how to find these y1, x1 coordinates. For all x coordinates, we move from left hand side to right hand side, and for all finding y coordinates, we move from downward direction to upward direction. Therefore, y1 is equal to b by 2, and what b we use it to find the area, that b will bring here, therefore 12 by 2, that is equal to 6 centimeters, and a1 y1 is equal to 48 into 6, which is equal to 288 centimeter cube. Similarly, coming to the part 2, as it is called horizontal rectangle, my area A2 is equal to L into B, my area is 14 centimeters and my B is 4 centimeters. Therefore, I will get 56 centimeters square, and to find the second coordinate of y direction for a horizontal rectangle, that is y2 is equal to b plus b by 2. Therefore, 12 plus 4 by 2, after simplifying this, we will get 12 plus 2, that is equal to 14 centimeters. And a2 y2 is equal to 56 into 14, we will get 784 centimeter cube. Now, utilization of this a1 y1 and a2 y2, my dear students, we need to find the area moment of inertia. Let us see that one. Utilization of a1 y1 and a2 y2, we need to find y bar, that is y bar is equal to a1 y1 plus a2 y2 by a1 plus a2. Therefore, y bar is equal to 288 plus 784 by 48 plus 56. Now, after simplifying this, adding 288 and 784, and again adding in the denominator portion 48 plus 56, divide this numerator with the denominator, we will get y bar is equal to 10.3 centimeters. Now, as I told you that the given T section is symmetric to y-axis, hence x bar is equal to 0, my centroid of the given T section can be written as the centroid of given T section C of x bar comma y bar is equal to C of 0 comma 10.3 centimeters. So, if you look at this answer, my dear students, this is what is known as the centroid part. So, in order to find the area of moment of inertia of any simple figure, first of all, we need to find the centroid. So, this is up to this as usual. The centroid of given T section, as it is considered as a simple figure, that is given by the centroid C of x bar comma y bar of a given T section is equal to C of 0 comma 10.3 centimeters. Now, our ultimate article is to find out the moment of inertia of a given T section with respect to x axis. You may ask one doubt in this particular context. What is that? No, why you are not writing moment of inertia of a given section with respect to y axis? I already told you that in the beginning, the given T section is symmetric to y axis. It is not symmetric to x axis. If it is symmetric to y axis, x bar is equal to 0. If it is symmetric to x axis, y bar is equal to 0. But in the present problem 2, the given T section is exclusively symmetric to y axis. That is why x bar is equal to 0. Therefore, I could find the centroid of a given T section C of x bar comma y bar is equal to C of 0 comma 10.3 centimeters. And the moment of inertia of a given T section with respect to x axis is to find that we have a formula that which is known as I double x is equal to I1 double x plus I2 double x. Now again we have to find I1 double x and I2 double x, and after finding I1 double x and I2 double x, adding both of them, then we will get this I double x. That we will see now. Now, determination of I1 double x and determination of I2 double x. So how to determine both the parts here. And I1 double x, we have a stipulated formula that I1 double x is equal to Ix1 x1 plus A1 d1 square. Bring all the values. Ix1 x1 is equal to 1 by 12 into LB cube. And after simplifying the L value and B value of the T section of the first rectangle, we will get 576 centimeter to the power of 4. And D1 is equal to y bar minus y1, that is equal to 10.3 minus 6, which is equal to 4.3 centimeters. This y bar is called centroid, in centroid C of x bar y bar. That y bar coordinate is 10.3, we got it centroid. Therefore, y bar minus y1 is equal to 10.3 minus 6, that is equal to 4.3 centimeters. And I1 double x is equal to 576 plus 48 into 4.3 whole square. This substitution is according to this formula. What is this? IO x1 x1 is equal to A1 d1 square. Therefore, I1 double x is equal to, I1 double x is equal to 1463.2 centimeter per. Similarly, we need to find a determination of I2 double x, that is I2 double x is equal to Ix to x2 plus A2 d2 square. Therefore, Ix to x2 is equal to 1 by 12 LB cube. This Ix to x2 is exclusively belonging to the second portion of the given T section, that is horizontal rectangle. Therefore, Ix to x2 is equal to 1 by 12 LB cube, which is equal to 74.66 centimeter to the power of 4 after substituting the L and B value in these particular places. Now, D2 is equal to Y2 minus Y bar, which is equal to 14 minus 10.3, which is equal to 3.7 centimeters. and I2XX is equal to 74.66 plus 56 into 3.7 whole square. This substitution is according to this formula. Then that is equal to I2XX is equal to 841.3 centimeter to the power of 4, and bring the value of I2XX and I1XX. Substitute in this formula, we will get I XX is equal to I1XX plus I2XX, which is equal to I XX is equal to 1463.2 plus 841.3, and after simplifying this, the total value is I XX is equal to 2304.82 centimeter to the power of 4, which is known as the exclusive value of area moment of inertia with respect to a given T section, and that is denoted by I XX is equal to 2304.82 centimeter to the power of 4. This is the way of calculating the problems towards the determination of area moment of inertia with respect to simple figures and composite figures, etc. And the determination of area moment of inertia by the utilization of composite figures, that episode we will see in the next video lecture. Thank you very much.